Hi everyone, I'm Li Shenzhou from the University of Michigan. Today I'm going to present our paper, RF Echo, a non-life-size indoor localization system using a low-power active RF reflector ASIC design. Location-based servers are growing recently with the increasing market in Internet of Things. It is predicted to have more than 2,000 million users and more than 1,000% growth in the market from 2012 to 2017. A wide variety of applications such as intelligent shopping mall and warehouse, or some public safety tracking applications are coming to our world. There are lots of commercial localization systems in the market, but they are either too expensive or not suitable for indoor usage. For example, GPS system has a very good surface area, but it has poor indoor accuracy. Most of the indoor localization systems, such as Wi-Fi or Bluetooth nowadays in the market, are receive signal strength indicator based. Its typical accuracy is in the order of meters, and the coverage area is limited. Ultra-wideband system has been an attractive solution for indoor localization system. It has good accuracy and immune to multipath effect. However, its maximum transmit power and distance is limited due to the large bandwidth. In addition to that, in order to achieve certain SNR and the timing synchronization, UWB system normally requires long integration time. Thus, the system complexity and energy consumption is high. We need a ubiquitous localization-ready system to enable more location-based service. I'm going to talk about some constraints for such a system. First, the tag form factor needs to be small. Similar to our smartphone recently, the tag size mainly comes from the battery, meaning that we need a low-power tag design to reduce the battery dimension. Second, in order to allow massive deployment of IoT devices and the fast-growing market, we want the tag to be low cost. In other words, the tag design cannot be too complicated. For some first responder applications, such as firefighter rescue operation, we want the system to be rapidly deployable without infrastructural investment. And of course, we always want good accuracy. Our target is in the tens of centimeter accuracy in the indoor non-life-size condition. We introduced RF Echo, a RF localization system with 90-meter distance in line of sight and up to 40-meter distance in non-life-size condition. RF Echo has an ASIC design tag, and then the anchor consists of a USRP and a laptop. The system has pretty good accuracy and a low energy consumption tag with only 80 microjoule per localization fix. With a small size coin cell battery, the tag can perform more than 100 million times localization. The basic ranging idea of RF Echo is to acquire round-trip time of flight, which is similar to a radar system. The anchor sends a 2.4 gigahertz OFDM channel sounding signal to the target and listen to the reflected signal. By comparing the transmit and reflected signal, the anchor can calculate the channel impulse response and the time of flight. However, if we have other objects that also reflect the ranging signal as shown in this figure, then we will get a combined channel impulse response which contains with the target and non-target reflection. The time of flight calculation will be more difficult due to those interferences. RF Echo uses an active reflector tag which, with the frequency conversion to distinguish the target from those unwanted reflection. As we can see from this three-dimensional figure, the active reflection signal and the passive reflection signal are separated in frequency domain. As a result, our anchor will only need to listen to the frequency band where this active reflection is, and then we can eliminate the interference from those passive reflections. So we can focus on dealing with the multipath. The active reflection tag not only solves the interference issues, but it also increases the operation distance by amplifying the reflected signal. The tag is an all-analog design, which has a deterministic delay without any timing ambiguity. We choose 2.4 gigahertz for the transmit and 900 megahertz for reflect in order to stay closer to ISM band for higher power transmission. And also, the OFDM ranging signal can also help us eliminate the inter-symbol and inter-carrier interference. This diagram shows the architecture of the anchor and the tag. We implement this anchor using a USRP and a laptop, and the tag is a custom-made chip. RF Echo relies on asymmetric communication to reach the low-power tag design and long operation distance, meaning that all the complexity should be pushed to the anchor side. The anchor has a high transmit power and very good receive sensitivity. In contrast, our tag has a very low power and simple design. RF Echo ranging starts from the transmit OFDM symbol, passing through a front-end synchronization module, and then being up-converted to 2.4 gigahertz. This power amplifier has 30 dBm output power. The signal will then travel through a multi-path channel and then reach to the tag. The tag will then do the frequency down conversion to 900 megahertz, and then passing through some amplification stages. The reflected signal will then travel through another multi-path channel and then reach to the anchor. The anchor will then analyze and comparing the transmit and receive signal to get the channel impulse response and the time of flight. Thanks to the frequency down conversion scheme, the reflected signal will experience actually less path loss than the transmitted 2.4 gigahertz signal. And we can relax the transmit power spec on the tag. Another big advantage of the reflection scheme is to eliminate the need of timing synchronization between different devices, which has always been a challenging problem in designing a localization system. This allows us to design a tag without any timing reference circuitry, such as PLL or crystal oscillator, enabling a low power, low cost, and even smaller form factor tag design. This figure shows the real capture ranging waveform and the detail inside our time of flight estimation block. First, due to the uncertainty of LO down conversion frequency on the tag, we will have carrier frequency offset in the reflected symbol. In order to prevent OFDM symbol from the loss of orthogonality, we need to compensate this CFO. So we manually added a pilot tone inside our OFDM symbol, and then we can estimate and compensate the CFO. Second, we have cyclic prefix to avoid inter-symbol interference. So we need to remove it from our OFDM symbol before we do the channel impulse response calculation. Then we compare the transmit and receive OFDM symbol by doing a division in frequency domain, and then we can get the channel impulse response. Later on, we're passing through an IFFT block, and then we can get a time domain channel impulse response. This time domain channel impulse response is the real-world capture data, which showed a good example of this multi-path and the direct path. Next, I'm going to talk about the relations between operation range, signal bandwidth, and localization accuracy. As we know, the higher the distance resolution can give us better localization accuracy due to the ability of distinguishing direct path and multi-path. However, the resolution is proportional to the signal bandwidth. Thus, we need a large bandwidth if we want a high accuracy system. UWB usually utilizes gigahertz bandwidth to achieve sub-centimeter accuracy, and the conventional FMCW radar distance resolution equation is shown here. Problem of using large bandwidth is the relatively low transmit power is allowed, which limits the operation distance. In other words, if we want to transmit large power for a longer operation distance, then we need to stay in sub-10 gigahertz ISM band, which has limited bandwidth available. So we actually tried this concept in designing our RF ecosystem, which only uses 80 megahertz bandwidth. We investigated in a time-of-flight estimation enhancement method via neural network to achieve similar accuracy compared to the wideband state-of-the-art system. So the first question of using neural network will be, what's the training data set? We examined the channel impulse response in both linear domain and log domain as shown in this figure. So this black line indicates the ground truth distance at 62 meters. And this blue curve is the linear domain CIR, and this red is the log domain CIR. As we can see from those small blue cross, if we are only using 80 megahertz sampling rate to train our neural network, then our localization accuracy will be limited to several meters. So first, we do an interpolation in order to do a final training to our neural network. And second, the main task of doing neural network is to figure out the first cluster, the cluster in CAR, which represents the arrival of the direct path. As we can see in this log domain CAR can actually emphasize the rising edge of the signal from those noise. And thus, it can help neural network to learn and to distinguish this signal arriving pattern. Our neural network has a two-layer, fully connected feed-forward structure. It has 48 and 16 neurons in the first and second hidden layer. The neural net is trained with a small window around the first cluster in the CIR to avoid overfit. Our training data sets are generated in MATLAB with a channel model from ITU. The synthesized CIR here shows that it can model the multipath effect and the delay spread pretty well. So there's no need of collecting real-world data before deploying our system, making our system to be rapidly deployable. This right-hand side figure shows the overlap of 20 synthesized CIR with random delay spread and the random multipath, and they are all at the same distance. As we can observe, they all have the similar rising edge pattern in terms of the arrival of direct path. Thus, neural network can help us efficiently figure out this rising edge and the time of flight. So we train our neural network with 500,000 samples. In addition to applying neural network and interpolation, we explore the usage of Bootstrap aggregating method and symbol combining. We train 3 neural network models with independent CIR in different portions of the pattern. We then compute the neural network output confidence based on the combination of these three models. Another technique is the symbol combining. We can either do coherent combine to enhance our SNR, or we can do the neural net weighted symbol combining to increase our accuracy. As shown in this figure, the x-axis is the number of combined Ophidian symbols, and the y-axis is the standard deviation of error. We can see that if we increase the combined Ophidian symbol, our standard deviation error goes down. Next is the low-power tech design. We designed and fabricated this chip in TSMC 180 nanometer technology. It's a very simple design which contains LNA, mixer, and local oscillator, and a variable gain amplifier and a power amplifier. In order to have a small form factor design, we minimize the off-chip components such as crystal and any matching network. And we use the free-running LC oscillator as our local oscillator since it has pretty good phase noise performance. This VGA has 4 gain level settings and provide up to 60 dB RF gain, which can give us large dynamic range on the tag. Now, I briefly went through all the techniques that we implemented in our RF ecosystem. I'm going to show some evaluation results. So for more details, please refer to our paper. This is the ASIC tag performance measurement. The tag has a 62.8 milliwatt power consumption. It has pretty good on-chip impedance matching, and then a pretty good linearity up to 0 dBm output power. And this gain versus frequency plot shows that our tag has sufficient bandwidth, 80 megahertz bandwidth, around 2.4 gigahertz. And the total noise figure is around 5 dB. This is the neural network output confidence of the real-world captured data in both line-of-sight and non-line-of-sight condition. The blue curve is the channel impulse response, and the red curve is the neural network output confidence. As we can see that the neural network can give us an accurate estimation of direct path time of flight in both line-of-sight and non-line-of-sight condition. We also tested our system in non-line-of-sight multipath rich environment, such as in the office, and also in non-line-of-sight multipath light environment, such as a long hallway with some blockages. In this figure, the x-axis is the ground truth distance, and also here. And the y-axis is the measured distance. As we can see, our system maintains pretty good accuracy across those long distance. This CDF plot shows the accuracy improvement with symbol combining. Take the challenging office environment as an example. We can actually reduce our ranging error from 1 symbol to using 10 symbol combined. This is a 2-dimensional evaluation result in Michigan EECS building. We tested both line of sight and non-line of sight scenario. This black star sign shows the anchor positions, and this blue box is, inside this blue box is the line of sight testing environment as some pattern on the ground. And this green box shows the non-line of sight testing scenario with the tag inside the classroom and anchor outside the classroom. And this wall between classrooms is made of brick and wood. And we can show that, we can see that here, the total overall result can give us like pretty good ranging accuracy. So here's the comparison table with some state-of-the-art localization system. We propose an active reflection scheme and neural network time-of-flight estimation. Thanks to the active reflector and the asymmetric scheme, our system can operate in large dimension compared to other systems. By getting rid of the long integration time and the timing synchronization between devices, our system can have a low localization acquisition time. So we have 20 microseconds per OFDM symbol. Due to the low acquisition time and the low power tag design, our tag energy consumption is more than 100x lower than other systems. The tag can perform more than 100 million times localization with a small size coin cell battery. It can sustain for more than 15 years if we do localization per 5 seconds. In conclusion, RF Echo is a long-range, low-power, low-cost localization system with good accuracy, which can support the growing location-based market and enable more applications. Thank you.